Okay, hello. Sorry again, I'm late, as per usual. This is the last of the lessons before the exam tomorrow, and really, I don't want to take too much time away from your revision. If you're looking through past paper questions, reading through the textbook, so just a few quick tips. Okay, one of the things that people have been writing in the comments in the website, remember that was an anonymous form that you could fill in, was talking about an open-ended question. So what I've done is I've written an open-ended question with two possible answers, and of course, well, in fact, why don't I just show you? So this is something that's been worrying some people, open-ended questions. This is my example. The question says, the diagram below shows the typical stopping distance for a car. Now it's travelling at 30 miles per hour in dry conditions. Using your knowledge of physics, and this is always what's mentioned in the open-ended questions, comment on how the values shown might change in wet conditions. Now, one thing I would say about open-ended questions is just remember your time. So if you were doing a numerical question, let's say there was a question which was an electrical circuit, and maybe in part A we had to work out the current in the circuit. We know the resistance of a lamp or resistance of a resistor. We have to work out the voltage across that component. Then of course, and this isn't the answer to the open-ended question, but if we did have an electrical circuit and let's say the current, we've just worked out that the current was 3 amps, the resistance is 10 ohms, and of course that means that the voltage across the component is 30 volts. Why I'm showing you this is what I've written is worth 3 marks, and that was done in under a minute. So just be aware of your time. Open-ended questions, they'll be worth 3 minutes. Now there could be anything up to 2 of these, but don't spend, I was going to say hours, you don't have hours, but don't spend an awful lot of time where you could be getting marks elsewhere. Okay, be aware of time, and it's always a question that you could come back to. You could maybe make a start on it and just check your answer at the end, but yeah, just be aware, as I said, when you're working this out, 3 marks there very, very quickly. And of course there could be marks available to you in an awful lot less time than the open-ended questions. Obviously you want to get through all the questions tomorrow, but let's see, we'll get back to this question. So we've spoken about timing. Now, as you can see, this is a question that's talking about stopping distance of a car, and of course the stopping distance will be the thinking distance. Now this is out of the highway code, so for dry conditions for a typical car and so on, the thinking distance is 9 meters. Now what that means is that's before you actually apply the brakes, so while the person's reacting, I guess you could work that out from distance is speed times time. So if you know the speed, which is 48 kilometers per hour or 30 miles per hour, multiply that by a typical reaction time. That gives you the thinking distance before the brakes are actually applied. If they're applied, then you've got the braking distance, and of course at that point the speed would be coming down. Add the braking distance to the thinking distance, and you have the total stopping distance. And the question's asking how, well, you need to use your knowledge of physics and comment on how this would change in wet conditions. So let's see, one possible answer is, if I can find it, it is this one here. Another thing people have been asking about is whether I would be doing higher physics next year. So yeah, we're hopefully going to be doing higher physics as well. I'll be hoping at that point to have a faster computer. Now, what does this answer say? Now, I did write this, but I wouldn't be expecting too many marks. The answer says, the car will skid in the rain because the road will be more slippy, so the stopping distance will be much bigger. I guess that's true. Bigger cars will have an even bigger stopping distance because they're heavier. I guess something we'll talk about is how to avoid losing marks in your exam, and one of the things is, of course, make sure you know what you're answering. This second sentence is talk about big cars, maybe have a larger mass. If they had a larger mass, I guess they'd have more kinetic energy and so on and so forth. I've not even spoken about energy. I've not mentioned forces. I've not mentioned friction. Even more importantly, the second sentence doesn't actually answer the question. It's not talking about the road conditions and how those road conditions would affect the stopping distance. So obviously that's not answering the question. You'll get no marks for that. The first sentence, which says the car will skid in the rain, I guess that's true, but what I'm not doing is I'm not using physics terms. I'm not mentioning, as I said, friction or energy or possibly the work done in order to stop the car, or I guess how much kinetic energy that the car has, and so on. This is not a great answer. So what you really want to do is, of course, you're using your physics knowledge. Maybe if we can get an equation in there, if we can use some of these terms about kinetic energy, work done, frictional forces, and so on. Now, I do have a better answer. Again, this, because of the limited space at the top, I'm not saying this is the perfect answer. Now, what I have done is I moved that. It's the first time 5-6 weeks that I've done that. I meant to move the pointer. So this is a better answer. As I said, I'm limited by the space at the top of the screen. There are still a few things I would say about this one which makes it not perfect as yet. Now, remember I said that stopping distance, that's equal to the thinking distance plus the braking distance. So the thinking distance, at that point, the car's still moving at constant speed, and its thinking distance from distance is speed times time would be that constant speed multiplied by the reaction time. So if you're assuming that in wet conditions the driver would have the same reaction time, then of course their speed would be constant, the reaction time would be constant. So as I've said in the first sentence, the wet road will not affect the driver's reaction time, so the thinking distance will not change. After that, of course, I've mentioned the braking distance, and of course the braking distance that will change. And the reason, of course, it will change is mainly because of this force of friction. Now remember, of course, that what's staying the same as well is the speed of the car. That's staying the same at 30 miles per hour. And I've said the braking distance will be greater, and the work done in stopping the car, EW is F times D, will be the same. So of course, if it's moving at 30 miles per hour, it'll have a certain amount of kinetic energy, and that'll be constant because the velocity hasn't changed and the mass of the car hasn't changed. So it has a certain amount of kinetic energy, and therefore it would take that amount of energy in order to stop the car. That's how much work would need to be done. So what I'm saying here is that the work done in stopping the car is a constant. And therefore, if the frictional force, this force F, frictional force between the tyres and the road, if that's decreased, then of course that's the force which is applied to the car in order to stop it. If that force is decreased, then therefore the distance has to increase in order for the work done to be constant. Now, what else have I said? So work done is force times distance will be the same, but with a smaller force of friction between the tyres and the road, the distance taken for the car to brake will increase. Stopping distance, so we've said before, stopping distance is the thinking distance plus the braking distance. So overall, the stopping distance will increase in wet conditions. Now, what I've not done is I've not written the perfect answer, but what I have done is, of course, I've used these physics terms. I've mentioned the force of friction. I've used an equation, work done as force times distance, but what I should have really done is that I should have mentioned, where I said the work done in stopping the car. So I have said that the work done is EW, of course. But I guess what I've not done is I've not said that this F represents the force of friction. Now I know what you're thinking, you know that, and I'm sure the marker knows it, but it would need to be stated clearly. So you could say that the work done in stopping the car, EW is equal to FD, which is equal to the force of friction multiplied by the distance. So I guess you would explain what these different terms mean. So that's one thing that I could have done. But as I said before, it's your chance to use your knowledge of physics. Try and explain, if you can, using an equation, but just make sure that you're explaining the different terms within that equation and that you're using these physics terms. Okay, so obviously this is a better answer than the first one. Now, the second thing I wanted to talk about was definitions. Now, I don't want to go over the whole list, so I've only got 4 slides to show you with definitions on them. And the first one, let's see, is this one here. Now this is one where we do learn an equation in higher physics, which actually makes this much easier to remember the definition. And of course, some of our definitions can be worked out using equations, or can even be worked out by looking at the data sheet at the start of the test, looking at the units. And I'll talk about that later. This one, I guess we just need to remember. So the definition for voltage is that the voltage of a power supply, or the voltage of a battery or cell, in this case I'm talking about a power supply, so the voltage of a power supply is the energy given by the power supply to 1 coulomb of charge. So that means if we had a 9 volt battery, then that 9 volt battery would supply each coulomb of charge with 9 joules of energy. Okay, and what I've said down underneath is that 1 volt is equivalent to 1 joule per coulomb. Okay, as I said, in higher physics, there is an equation that goes with that one. Makes it much easier to work out. But if you can remember, 1 volt is 1 joule per coulomb. Okay, second one looks a little bit like this. Current. Now this one, we actually can work out using an equation. So remember the equation which links current, time and charge is Q equals IT, and therefore I is Q over T. And of course we know that Q is the charge in coulombs, we know T is time in seconds, and I is of course the current in amps. And current, that's the charge transferred in 1 second. You could also say the charge transferred per unit time, because of course the unit of time is the second. So current is the charge transferred in 1 second. And that, as I've said at the bottom, 1 amp is the current that's produced when 1 coulomb of charge is transferred in 1 second. So there we go. There's the unit of charge, which is coulombs. And as I said, dividing by time in seconds. Okay, so the charge transferred in 1 second is the current. Now, as I've said, I'm not going through all of these. But what I would say is just make sure there will be a list which comes up, and just make sure you look through your notes. And again, it's not an exhaustive list, it doesn't mention everything, but make sure you know at the very least these definitions that I'm talking about. Now this is actually something which came up in last week's lesson. The half-life. This is one that's often asked. So the half-life of a radioactive source is the time taken for the activity of a radioactive source to half. Of course, we can say it a second way. The other way that we can mention this is that it's the time for half the nuclei in a radioactive source to decay. Okay? Personally, if I was asked what is the half-life, the definition of half-life, I would just go for the first one. But it's important to remember that you're talking about the activity, the time for the activity to half, not anything else. It's possible to write an answer close to that, so maybe talk about if someone had said the time taken for the radioactivity to half, wouldn't get the answer, or the time for the radiation to half, wouldn't get the answer. Could even mention the time for the count rate to half, not going to get that. So we'll talk about the activity. So half-life is the time taken for the activity of a radioactive source to half. What I've got in the next one is just some work that you could be doing. As I said, I don't want to take too long, because of course I'm hoping that you might want to look through some of the videos. It's up to yourself. Of course, I've gone over as much as I can in 5 weeks, but you'll want to spend some time looking through notes, looking through past papers. So this is another list of things which could come up. Pressure, again, that's one which we could use an equation. P is equal to F over A. And we did say about current, you can use that Q equals IT equation. This one, of course, is pressure is equal to force divided by area. Now you could use that if you were asked what the definition of pressure is. Then of course that's the force, and of course we know that that's in newtons divided by the area, which is in square meters. So you could just say it's the pressure is the force per square meter, or you could say it's the force per unit area. Okay. The next one, of course, we've spoken about most of these. Vector and scalars, you need to know the difference between those, of course, and we know that vectors have magnitude or size and direction, and that scalars just have magnitude or just have size. There was a question before about the light year, which is a distance, of course, and it's the distance travelled by light in 1 year, and that's in air or in a vacuum. Okay, so of course light year is a distance. A specific heat capacity. Let's see, what do we want to say about that one? I guess what we could do in that one is to look at the data sheets. If you're struggling to remember that one, then if you were to look at specific heat capacity, you would see that the units in the data sheet, joules per kilogram per degree Celsius. Okay, so looking at that, if you have to the -1, that means you're dividing. So joules per kilogram per degree Celsius. And it's basically, well, we know that joules, that's for energy, kilograms is mass, degrees Celsius is temperature. The specific heat capacity, the value of C, which is in the equation, if you remember, EH is Cm delta T. Okay, so the specific heat capacity, that's just the energy, obviously measured in joules, the energy which is required to increase the temperature of 1 kilogram of a material by 1 degree Celsius. Okay, so the energy it takes in order to increase the temperature of 1 kilogram of a material by 1 degree Celsius. We've also got the specific latent heat, that's in joules per kilogram, and of course that one, that's used in the equation EH is ml. So when we're talking about the specific latent heat of fusion, that's talking about something changing from a solid to a liquid. Again, remember joules, of course, are for energy, the unit of energy. So specific latent heat of fusion, that's the energy taken in order to change the state, say, of 1 kilogram of a material from a solid to a liquid. And if we've got specific latent heat of vaporization, that's just the energy in joules that's required to change the state of 1 kilogram of a material from a liquid to a gas. Okay, so you can get some information, I guess, from the units. What else do we have? Gravitational field strength. Well, I suppose we know W is equal to mg, and therefore, of course, G is W divided by M. Of course, that W, that's a weight, that's a force. So we could just say, of course, since that's the force, it could be that we just mentioned it's the force per kilogram experienced by an object, I guess. So it's basically to do with the force per kilogram, or the force per unit mass experienced by an object at that position in space. The other two I spoke about in the last lesson, we spoke about refraction, and that was related to, of course, we don't want to mention, although most of the time, 99% of the time, of course, associated with refraction would be the light bending, say. But remember, I mentioned this definition last week, that we were talking about the change in speed. Let's say if we're talking about light, the change in speed of light as it passes from one material to another. We also mentioned ionization. Looking at a marking scheme, you'll see that it mentions for ionization, it's when an atom gains or loses electrons. That would be enough if we were asked for the definition of ionization. So when an atom gains or loses electrons. I went into a little more depth and actually spoke specifically about ionization when the alpha particle was ionizing a neutral atom. And I was talking about the alpha particle removing an electron, an outer electron, from the atom in order to leave it positively charged. Okay, so a bit of work for you to do, just to look through the definitions. Before I actually started this live lesson, what I did is I had a video which was on YouTube, which I've actually taken down for, I think I mentioned at one point using a pencil to draw graphs. And I was very embarrassed, of course, by the instructions at the start, which mentioned to use a red pen. So not a red pen, a marker, use a red pen. It mentions using a black pen or a blue pen. Now that reminds me, of course, read the instructions at the start of the test, and it will mention using a black pen or a blue pen. Something I think I'd said in that lesson was it's possible to get these pens which rub out, of course, and when you're drawing a circuit diagram or maybe drawing a ray diagram, make a mistake, then if it's just a small mistake, of course, that could get rubbed out and redrawn with that pen. Of course, in the the exams, you'll have seen in the past papers, if you completely mess up one diagram, there will be a spare at the back. Anyway, in this lesson I'd written a few points. I'd written 9 points, all about avoiding silly mistakes. So the last thing I wanted to do was just to go through this list. Number 1 in the list, I almost lost mine. I had mentioned this thing here, and I've not used it tonight. Remember a calculator. And then, well, as important as remembering a calculator, remember your calculator. And of course, this button here, times 10 to the power of. You could have been working with a calculator all year and have to borrow the teacher's, a friend's spare calculator. You don't know where that button is, or some other buttons which are important. That's a lot of stress we don't need. So I would suggest, once you've done your revision tonight, get that in the bag, in the pocket, wherever it needs to be, so that you've got it for tomorrow and you've done with that stress. Number 2 on the list was to read the question carefully. Now, I've spoken about the open-ended question and how it's possible to maybe even include some good physics in your answer, but if it's not answering the question that's been asked, you won't get marks for it. Another thing, look at the number of marks available in the question, and that will give some indication as to, I guess, how much work needs to be put in to get the marks. A simple question, remember I showed you the question before, using V equals IR, that could be worth 3 marks. It would be worth 3 marks. If it's a 4-mark question, then maybe there's an additional calculation that needs to be done. It could be a heat equation, but also you've got to calculate a change in temperature. That's maybe not a good example, but there will be a difference between a 3-mark question, numerical question, and a 4-mark question. There would be an additional calculation, so just look for that. Number 4 on the list is to use your relationship sheet. Now, I've said it a few times, this is not the relationship sheet. Of course, you will be given that, so that's one less thing to worry about. Don't worry about the relationship sheet. There will be one with the exam. But this is a sheet which is on my website, and it's the help with relationship sheet. You'll see at the top, basically it gives you all the different units which are used in the equations in alphabetical order. So it tells you the A is acceleration, and it's one thing to know how to manipulate the equations in the relationship sheet, but of course you need to know the units that go with them, or else you're going to lose marks. So it's something you could spend some time on tonight. So yeah, the units for acceleration, ms to the -2. Sometimes you'll see that the same letter is used more than once. So in fact, capital A is used twice. In one of the equations for activity, A is n over T. This is talking obviously about ionizing radiation. It represents activity, and that's in becquerels, whereas we've actually mentioned another equation today, which is with power. Power is force over area. So the A in those two equations, not the same. The second one, force over area, area is in meters squared, as we said. Anyway, that's something just to think about. Think about looking at that sheet. Go through it just to make sure that you know all the different units. Where am I? I'm on number 4, multiple choice. What I'd written before was to don't look at the answers, not to look at the answers. What I meant by that was really, it's a good idea just to try and work towards an answer first before you pick your answer. Obviously, what I didn't mean was don't ever look at the answers. At some point you need to look at them and choose which one you think is correct. So multiple choice, try and work out what you think the answer would be first before, because obviously whoever set this exam, they don't want to give you the correct answer and 4 other completely wrong. They won't be obvious which of the answers are wrong, obviously. So it's a good idea to have an idea, I guess, of which one's correct, and then pick it. Right, what have I said? I've said look out for state, calculate, show, and justify questions. Now this is something I've spoken about throughout the lesson. Show questions, as I said before. What you really want to do is to give every single step in your calculation. If it's a question that's saying calculate and of course I wrote out the question before. V equals IR was, I can't remember what the values I used. In a calculate question, technically we're just looking for the final answer. Now, I wouldn't want you in the exam to just write the final answer. I would want you to write out the equation with the substitution, with the correct answer. Of course, remember your unit as well. But, and of course, while you're doing that, while you're doing all the working anyways, of course, if there's any mistakes, you will pick up all those marks along the way for the correct equation, for the substitution and so on. If you make a mistake, of course, you have no marks. But in a show question, if you just had the correct answer at the end, you wouldn't get the marks. It's really important in those ones to have all the working. But as I said, I would always make sure that you're including all the working anyway. Right, almost there. Don't get caught out by significant figures. I've said before, of course, that your final answer should have the same number of significant figures as the number in the question that has the least number of significant figures. As I've said, I've done 5 of these lessons before. There's no easy way of saying that. So if you look through the videos, you'll see what I mean. Remember the SI units, and that comes back again to that help with the relationship sheet. Okay, so in there I've mentioned what the symbols mean in the relationship sheet and also the units. It would be an awful shame in, say, a 3-mark question for you to remember the equation, the substitution could be perfect, you've got the right number as the answer in the end, can't remember the unit, and you would lose 1 out of 3 marks. So you would only get 2 out of 3. And last but not least, check your answers when you're finished. Okay, so hopefully you'll be left with a few minutes towards the end and you can just look through. So try and look through with fresh eyes. It's very, very easy, I guess, to assume that what you've written is correct. Okay, but imagine you're the marker, I guess, at this point. And just make sure, have you got the right equation? Are you using the correct numbers? Do you have the correct unit? Assume that you've maybe made a mistake, but make sure that you check your answers at the end. And unfortunately, that's us, which is quite sad because, yes, I have enjoyed doing this over the last few weeks. As I've said, there was a comment that was asking, would I be doing higher physics? So I'll certainly be doing higher physics next year, as well as National 5 again. Certainly not all within 6 weeks. Hopefully I'd be working that over a bit more time, so it's not quite so rushed and I'm not quite so busy. It has been an awful lot of hard work, but hopefully it's been helpful. I've had some lovely comments from people through the website who have been telling me that it has been of help. So, I'm trying to find my mouse. All I was going to do was to show you one last picture, which is, of course, to wish you good luck tomorrow. Okay, so that's it for me. And as I said, I will see you again next year. It's a long time to wait, but obviously after this you deserve a rest. And if you're doing any other exams after physics, I know it's the last exam for some people, then of course good luck in all of those as well. Okay, thanks very much for listening and good luck tomorrow.